Hi, my name is Uri Shtemer, and this is a joint work with Amos Beimel, Haim Kaplan, Yishay Mansour, Kobbi Nissim, and Thatchaphol Saranurak. This work is about dynamic algorithms against adaptive adversaries, and we provide both positive and negative results. Let me start with this motivation slide. So we all know that typically, when we design randomized algorithms, we assume that the internal randomness of our algorithm is independent of our input. And this is fine when we talk about offline or like one-shot algorithms that get their input, compute whatever they want to compute, output it, and that's that. But if you think about it, in online or interactive settings, this assumption is not always reasonable, because it could be that in an online setting, the algorithm outputs something, and then the next input that the algorithm gets may depend on the previous output that the algorithm gave out. And as a result, the next input may depend on the internal randomness of the algorithm. So the takeaway from this motivation slide is that we want to design interactive algorithms that guarantee utility even when their inputs are being chosen adaptively. So we are not the first to study this question. It's been around for a long time, and it's been studied by several different communities. The dynamic algorithms community, the streaming community, and related questions have been studied in the machine learning community and in the adaptive data analysis community. And in this work, we continue the study of this question for dynamic algorithms. Okay, so let me make the setting more explicit, and I'll compare what happens in the classical or oblivious setting to what happens in the adaptive or adversarial setting. Let's begin with the classical oblivious setting. We have here an algorithm that gets an input, and the input to this algorithm changes over time. And the algorithm needs to output, after every time the input changes, the algorithm needs to output a modified estimation or modified output for the whatever it needs to compute. A good example to keep in mind is the global mean cut problem. So the input to the algorithm is a graph. The algorithm needs to output an approximation to the size of the global mean cut in the graph. And then from time to time, the graph changes. Let's say each time step an edge is added or removed from the graph, and the algorithm needs to update its response. So in the oblivious setting, we assume that there is some fixed, unknown, but fixed sequence of input updates. And the algorithm gets to see these input output updates one by one. So in the beginning, the algorithm gets to see the first input update. The algorithm responds with its first output. Then the algorithm gets to see the second input update. The algorithm responds with the next response, and so on. Okay, that's fine. What happens here? We still have our algorithm, but now the input sequence is not fixed in advance. Instead, there is some kind of an adversary that chooses the updates adaptively as time goes by. So in the beginning, the adversary chooses the first update. The algorithm gets this update U1, responds with its first response Z1. Now the adversary gets to see this first response Z1, and based on Z1, the adversary chooses the next update U2. The algorithm responds with its next response, and so on. And as you can guess, the difficulty with this picture is that the inputs that the adversary chooses depend on the previous outputs of the algorithm, and as a result, depend on the internal randomness of the algorithm, and that's a problem. And the question that I want to be asking today is, what's the price we need to pay in runtime in order to be able to cope with the adaptive set? Or in other words, let's say I want to design an algorithm for some problem, for some dynamic problem. How much more runtime do I need in the adaptive setting compared to what suffices in the classical oblivious setting? Formally, we assume that there is some problem that we are interested in. For example, the problem of estimating the size of the global mean cut in the graph. Now we consider a two-player game between a randomized algorithm and an adversary. In the beginning, the adversary specifies the initial input x0. Then, on every round, the adversary chooses the next input update, and we can think about this input update as a function that maps inputs to inputs. So by specifying the next input update function UI, this effectively transforms the input from the previous input to the next input. So the adversary specifies this input update UI, the algorithm gets it, processes it, and responds with its next response ZI. And like we mentioned, the issue is that the adversary's choice for the next UI can depend on all of the interaction so far between the adversary and the algorithm. The goal of the adversary in this game is either to cause the algorithm to fail or to have large runtime. Okay, so that's fine. And there are like two naive strategies you can apply here in order to construct an algorithm that satisfies this definition. You could easily show that if your algorithm is deterministic, and if it solves the problem in the classical oblivious setting, then the algorithm also solves the problem in the adaptive setting. So that's a possible solution, but designing deterministic algorithms is often very costly. Okay, the second baseline solution you can think about is just on every time step, just run a static algorithm to solve the problem from scratch. So that would also work, of course, in the context of the global mean cut problem. What it means is that after every edge change in the graph, just recompute from scratch the size of the global mean cut. So that would work, but it will also be costly. What we want are solutions that run faster than these two naive strategies. And like we mentioned, the difficulty is that when you construct randomized algorithms, you need to be careful because as time goes by, the adversary might learn information about your internal randomness, and then the adversary may use this in order to cause you to fail. Okay, so I'll first present a statement of our positive results, then present a statement of the negative results, and then I'll tell you just a little bit about our techniques for some of our results. So our main result is we develop a generic transformation from an algorithm that works in the oblivious setting to an algorithm that works in the adaptive or adversarial setting. We use this generic transformation in order to obtain new results for the following three problems: global mean cut, all pairs effective resistance, and all pairs distances, where for this problem, we consider two cases. Either we want approximation ratio of poly log n, where n is the number of vertices, or we want the approximation ratio to be almost log n. And for all of these 3 or 4 problems, we get significant improvements compared to what was previously known. So that was what was previously known. These are our new results where, like we said, n is the number of vertices and m is the number of edges in the graph. Okay, here is a statement of our negative result. We show separation results in that we present dynamic problems which you could easily solve trivially in the classical oblivious setting, but no matter how you try to solve these problems in the adaptive setting, you must probably use polynomially larger runtime. And this is under some computational assumptions or alternatively in the random oracle model. To the best of our knowledge, this is the first formal separation between the capabilities or the needed runtime for dynamic algorithms in the oblivious setting compared to the adversarial setting. In particular, a byproduct of our separation is that we separate the needed runtime or the power of deterministic dynamic algorithms compared to randomized dynamic algorithms. And the reason is that, like we mentioned, a deterministic dynamic algorithm automatically works also against adaptive adversaries. And therefore, if we separated these two, then in particular, we separated these two. Okay. For our separation results, we consider two types of dynamic problems. We consider estimation problems, where the desired output is a number. And we consider search problems, where the desired output is not necessarily a number. So with our global mean cut example, if you want either the size of the global mean cut or an estimation for the size of the global mean cut, then that's an estimation problem. But if you want an actual cut, then that's a search problem. And I'll just mention that estimation problems are just a special case of search problems. And so getting negative results for estimation problems is potentially harder. Okay. Here is a statement of our separation results. This is our separation for search problems. For any constant C, we show that there is a dynamic search problem, let's call it Pn search, where n is a parameter controlling the instance size, that can be easily solved in the oblivious setting with amortized update time linear in n. But no matter how you try to solve it in the adaptive setting, it requires at least n to the c amortized update time. Furthermore, this holds even if the algorithm is allowed to spend exponential time for free in the pre-processing stage. Okay, that's our separation for a search problem. Here is a statement of our separation result for an estimation problem. We show that there is a problem, let's call it P and S, where again, n is a parameter controlling the size of the input, that can be solved in the oblivious setting with total time n to the sixth over n squared updates. But in the adaptive setting, it probably requires at least n to the seventh time over n squared updates, over the same n squared updates. So it's not as strong as our separation for a search problem, because first, here for any constant c, we could show a polynomial difference to the power of c. And here we only show this separation between n to the sixth and n to the seventh. And also here, we allowed the algorithm to spend basically exponential runtime for free in the pre-processing stage, and here we don't have that. Okay, so that's a statement of our negative results. Here are some of the ideas behind some of our results. So Like we mentioned, the difficulty in the adaptive setting is that the adversary might learn information about the internal randomness of our algorithm. So the idea behind our generic transformation is to use a technique introduced by Hasidim et al. To protect the internal randomness of the algorithm using differential privacy. So unlike the common application of differential privacy, which is to protect data, Hasidim et al. Used it in order to protect not the data, not the inputs to the algorithm, but just the internal randomness of the algorithm. And intuitively, protecting the algorithm, the randomness of the algorithm with differential privacy hides it from the adversary. And so intuitively, that kind of allows us to avoid or overcome the problems that pop up from adaptivity. So to formalize this idea, we use techniques from the recent line of work on adaptive data analysis by Georgetown et al. And Basili et al. So we adapt this technique of Hasidim et al. To protect the internal randomness of the algorithm with differential privacy. We adapt it to the dynamic algorithm setting, and we optimize it for our problems. And I'll just mention that following Hasidim et al.'s work, this idea of protecting the internal randomness of the algorithm with differential privacy was used by several follow-up papers in several different settings. Okay, so here is a more explicit statement of, or a simplified statement of our generic transformation. Let T be any parameter, and let A be an algorithm that works, a dynamic algorithm that works in the oblivious setting. We begin by initializing root T independent copies of algorithm A, each with its own independent randomness, and each initialized with the initial input x0. Now, for T time steps, we obtain the next update UI. We feed UI to all of the copies of algorithm A. And then we sample almost a constant number of the copies of A, query these sampled copies, aggregate the responses with differential privacy, and output the aggregated result as our current response. We do this for T time steps. After these time steps, we reset all of the copies of algorithm A, meaning we reinitialize them with the current input as their new initial input, and each copy we initialize it with a fresh independent randomness, and we then start back from here. In the analysis, we show that this algorithm satisfies differential privacy with respect to the internal randomness of the copies of algorithm A. This we leverage in order to show that the algorithm maintains correctness even in the adaptive setting, as long as algorithm A is correct in the oblivious setting. And the total time that we need for T time steps is during every time step, we query, let's say, a constant number of the copies of A. So during T time step, we query a constant number of the copies, so T times the query time. And throughout all of this phase, throughout the specific complete phase of step 3, we have root T copies. Each of them, we pay T total time, where T total is the total time needed for all of the T updates throughout this phase. So that's our total runtime for a phase. And from that, by choosing the parameter T appropriately, depending on T total and T query, which are the runtime parameters of algorithm A, you could already get non-trivial results for the graph problems we considered. But this does not yet get you to the bounds that I specified in the table before. For that, you need additional ideas. Specifically, in the paper, we show that the runtime of step 4 can be sometimes improved, because we don't need to actually reset all of the copies, or we can do something softer. Okay, so that's the idea behind our generic transformation. And here is the idea behind our negative result for search problems. Suppose that we have a hash function h mapping n bits to n bits, and suppose that this hash function can be computed in linear time on every point. We design a dynamic search problem in which the adversary is allowed to specify excluded or forbidden strings. Now, on every update, the adversary is allowed to add one more element to the set of excluded or forbidden strings. The algorithm, on every time step, it knows the set of forbidden strings. All it needs to do is to output some non-forbidden string with its hash value. That's all the algorithm needs to do. And indeed, in the oblivious setting, this is a trivial problem because the algorithm, on its first step, could just randomly sample one element x, compute its hash value, and then just output the random x that it chose with its hash value, and just output that for a very long time. And the reason is that if x was chosen at random, then the probability in the oblivious setting that x will be included in the forbidden set big X, that's negligible as long as the size of the forbidden set is not too large, which we assume. So in the oblivious setting, all the algorithm needs to do is just sample an element x, compute its hash value, and that's that. The algorithm won't need to compute new hash values throughout the execution. But in the adaptive setting, what the adversary does is on every time step, after you specify your chosen x and its hash value, the adversary would just say, okay, then that goes into the forbidden set. And then in the next iteration, the algorithm must come up with a new x and compute its new hash value. So in the adaptive setting, the adversary forces the algorithm to compute a hash value per time step, while in the oblivious setting, the algorithm just computes one hash value for all of the execution. To formalize this idea and to show that it works, we need to assume some properties of the hash function h. We can show that these properties we can show that these properties hold in what's called the random oracle model. Specifically, we need h. We already said that we need h to be computable in linear time, but we also need it to be what we call moderately hard, meaning that if you want to compute it, you must spend some noticeable amount of time. And furthermore, if you want to compute the hash function over several different inputs, then basically that's going to cost you as much time as to compute it individually on each of them separately. Okay. So that's our negative result for a search problem. In the paper, we show a more complicated negative result for a search problem where we add the additional requirement that exponential time in the pre-processing stage won't help the algorithm. And we also specify a separation result for estimation problem. To summarize, we present a generic transformation from algorithms in the oblivious setting to dynamic algorithms in the adaptive setting. This allows us to obtain new results, new runtime bounds in the adaptive setting for global mean cut, all pairs effective resistance, and all pairs distances. And under some computational assumptions, we present problems that separate between what can be done in the dynamic oblivious setting compared to the dynamic adversarial setting. And that's it. Thanks for listening.